Yeah, ladies and gentlemen, it's a great pleasure for me to welcome you again on this Wednesday afternoon to our hydrogen webinar about the dawn of the hydrogen economy. It's a great pleasure for me to welcome you on behalf of the different organizers. And also tonight we have a quite interesting program with quite interesting guests. So first of all, we will have a presentation from Silke Neuberger and from Manuel Langemann about the decarbonization of green hydrogen in Germany. Both of them are from RWE, and they will give us an update about the ongoing activities in one of the biggest energy utilities here in Germany. And then it's my great pleasure to introduce Dr. Monchi Marzouk. He's the former Tunisian Minister for Energy, Mines and Energy Transition. And he will give us an update about the role of green hydrogen in the Tunisian energy system. So therefore, we can get a good overview about what's planned and what's ongoing here in Germany and what's ongoing in Tunisia. As usually, we will have the two presentations, and afterwards we have the chance and the possibility to discuss a little bit about the upcoming points and the upcoming questions. So therefore, please do not hesitate to post any comments or questions or whatever you feel makes the discussion more interesting and more challenging into the YouTube chat area, and then we can pick this up and discuss this a little bit more in detail. Before I pass over to Manuel Langemann, I will just mention that next week, same time, same place, we will have two country reports. And we have two country reports, one from let's say New Zealand and one from the US, where we also get first information about the currently ongoing Inflation Act or Inflation Act from the US and about the ongoing activities there. So that's more or less what I can do. And from that time, I would like to pass now over to Manuel Langemann. Before that, I just would like to ask the translator if they can unmute, if this has not happening already so far, because I understood from my colleagues that the French stream is still very silent. So it might help if you unmute yourself and then the people can listen to your translation. So thank you very much for that. And now it's my great pleasure to pass over to Dr. Manuel Langemann, and he will then pass over to Dr. Silke Neuberger. And with this, just go ahead, and we are interested in your presentation about decarbonization by green hydrogen in Germany from RWE. The floor is yours.
Yeah, thank you very much for the nice introduction. I hope you can already see my screen with the presentation. And yeah, also from my side, a warmly greetings here from Germany, close to Cologne in my case. And I want to introduce Silke and myself. So we are working since 2021 in the Society of Generation. It's a society of RWE. It's the Generation Society, and so we are working more in the field of hydrogen, especially green hydrogen. So I will give you a short approach of the presentation we will do in the next minutes. So, for example, we will present the approach of the strategy of RWE, and speaking about the pilot plant in the next. So, and after this, we will show some typical details of PEM and alkaline electrolysis. Silke, she will present also some challenges of engineering, and maybe you know there are also some requirements coming up from the EU, which means that we also have to show what is the life cycle analysis of such a electrolysis plant, so regarding to the CO2 footprint. And after this, we'll give you a short overview about the permitting process, and finally we will close this session or this presentation with the conclusions. Yeah, first of all, I will show you here. You can typically see the situation currently in Germany. So the most of you know that since I guess it's 2020, it was in 2020 that the German government say that we should increase the industry for green hydrogen. With a capacity of 10 gigawatt. I guess in the beginning it was around 5 gigawatt, and during this new German government, they increased this target to 10 gigawatt. And this is a need or necessary to reducing the amount of green hydrogen greenhouse gases. And the green hydrogen could be useful in different sectors, for example, in the electricity and heat sector, in the steel sector, and in the chemical and industrial sector. And so this is also we in RWE, we want to be aligned with these targets. So, for example, we have our own targets, where we say that RWE wants to also increase or erect an electrolysis capacity until 2030 with 2 gigawatts. And the requirements and the basics are that we need a good regulatory and political framework, and also supporting or funding schemes where we can also realize reliable offtake agreements. So, and one of these approaches could be that the erection of large-scale electrolysis plants could be the key. For example, something like 100 megawatt plants. Here we'll give you a short overview about the different societies in RWE. For example, maybe you know also some of them. We are divided in, for example, in the renewables part, where we give me a second, I will present the laser pointer. So for here, in this case, we are have the renewables part where we are more focused on the wind and solar electrolysis energy supplying. And for example, Silke and myself, we are more dedicated to this part here in the middle. This is also dealing the different energies coming up from hydro or biomass, and we are more focused in the field of hydrogen, for example. Then we also have the Society of Supply and Trading, which are responsible for the trading processes and origination. And as you know, one of our old societies, it's called the RWE Power, and there we handling a lot of energy supplying coming up from coal and at least nuclear. So here you have a short overview about some of our key facts of the companies. And and what is important here on the slide, for example, here you get an overview of different of our capacities. These numbers are coming up from 2021. And as you can see it here, our core markets are also in Europe and more dedicated to Germany, the Netherlands, and the UK. But we also have some of our assets placed in the US, for example. And what maybe is also important to say is that we are also currently increasing different battery projects, for example, and also be involved in hydrogen projects, which you can see here from on the left bottom here, for example. And maybe one thing what is good to say at this point is that RWE wants to invest more than 50 billion euros in the Green Growing Initiative until 2030. So this includes also the supplying of renewables energy, and also the point that we want to increase our electrolysis capacities. So let me say some words to the strategy. We also have or try to find out what are the best the best potentials industries in Germany, for example. In our mind, it could be possible to substitute or to erect hydrogen energy until 2030, with a capacity of 113 terawatt hour, for example. And this is divided into as you can see it here, 3 different industrial types, for example, so for ammonia, for refinery and steel, for example. And only to show you some numbers, this energy demand in hydrogen with a capacity of 113 terawatt hour means that we need a hydrogen capacity of almost 3,400 tons of hydrogen per year. And this leads to the capacity target we want to achieve, for example, with 1.9 gigawatt or almost 2. And some of these electrolysis plants could be placed in different or in 4 different identified industry cluster around or in Germany. So this includes, for example, the northern Germany part, the Rhine-Ruhr area, the Rhine-Main-Neckar part, and so also the central Germany part. And as you can see it here, in the most cases, so the substitution of coal in maybe some iron refinery processes to make steel could be done by hydrogen, and this could be a good potential, for our industry or for the use of our green hydrogen, for example. And here is only a short overview about some of our hydrogen projects, which are placed in Germany, Netherlands, and the UK, for example. I will not name every one of them. For example, one of them is important, which is the GetH2 Nucleus project, which is placed in Lingen, for example. Currently, we are in a very detailed engineering process to erect finally 300 megawatt electrolysis plant. And what I can say to you right now is that we are currently in the construction phase of our pilot plant, which also include, for example, 10 megawatt of an alkaline electrolysis and 4 megawatt of an PEM electrolysis plant. So these are currently the ongoing process in Lingen, for example. And this is one of the projects which are presented here right now. And some of these projects, as well as the Lingen project here from GetH2 Nucleus, this is also funded by an IPCEI, by the IPCEI funding. And And then I will hand over to my colleague, Silke.
Hello, everybody. I will talk now a little bit about the pilot plant. This is our first project of the Hydrogen Hub. This pilot plant, as Manuel already mentioned, is based on 40 megawatts, and these megawatts are split in 2 different technologies. One is the PEM electrolysis, and the other one is the alkaline water electrolysis. We are building this plant, as you can see on the nice picture on our site in Lingen, where also the other electrolysis plant, the 100 megawatts, will be built afterwards. But this is our first project, and that's why we will talk today about this project. We as RWE decided that we will do as much engineering on our own as possible, so that we have a great learning out of this pilot project, and we can implement the learnings in further projects. The commissioning will take place at the end of this year. Next slide, please. Why does RWE build a pilot plant in Lingen? So one of the goals, or one of the major goals, is that we would like to compare the different technologies, the PEM electrolyzers on the one side and the alkaline electrolyzers on the other side. We would like to get out of the operation of these plants a deep knowledge of the electrolyzers and how the electrolyzers react with the surroundings, for example, the cooling water, the nitrogen plant, and the other things, and if it's possible to run the electrolyzer plants after a wind profile, because the electrolyzers which RWE wants to build will always or often run after a wind profile. And there are certain times under which the electrolysis needs to react. And therefore, we will try to do a lot of tests with our pilot plants to get detailed knowledge out of that. Yeah, of course, we would like to improve by this project our internal processes and our project handling. And this is the start for our value engineering, which we are doing then. In the end, we would like to implement principle of Industry 4.0. Yeah.
Okay, I will go further with some details of PEM and alkaline electrolysis. Okay, now you can see a slide which shows all the three typical or the main electrolysis types. So, for example, well known on the alkaline, PEM, and SOEC. And here I will only give you a short overview about the difference between all of these electrolysis types. So, for example, what you can see is here all of these electrolysis technologies includes different usage of different materials. So maybe in the case of PEM electrolysis, titanium and iridium and platinum are important for the stacks. And in the case of, for example, of the alkaline one, which you can see here at the first, nickel and steel are a very used material. And on the other side, in the case of the SOEC, you can see there are different types of metals and other materials which lead to ceramic materials and which are useful for the high or for the requirement of the high temperature. And all of these different materials, what I want to say is includes also different cost structure. So this means for example, in the case, for example, of iridium, this is, I marked this here as a critical material regarding to this status as a raw material, only to give you the information that we completely on the world, we I guess we have a yearly production of around 8 tons of iridium. So, and this amount of iridium is not going only in the field of electrolysis, also other electronics and other devices needs this material, for example. Yeah. Here I will only show you the short overview about the parameters, the different parameters regarding to each technology. I will not go in here very deep. A lot of you people, I guess, you will, you do not see this information for the first time. For example, what is important in the case when we see this part here in the current density, this is an important specification regarding to the to every technology. So, for example, in the PEM case, you are able to run the electrolysis cell or stack in higher current density regions compared to alkaline, for example. Stack efficiency could also be higher. And what is another important specification is the degradation rate, for example, and the lifetime, which is a result of the degradation, for example. And here we have also some difference. And from the literature, it's mostly it's well known that the degradation rate of the PEM electrolysis could be a little bit higher than in the case of the alkaline one. I want to show you here some the overall plant overall electrolysis plant, for example, with the typical components we are using in such a system, for example. So the heart is the electrolysis stack, which you can find here in the middle, but to prepare the process water, for example, a lot of other components are needed in this chain. For example, the water polishing process is the first step. Then we have the separator, for example, where oxygen and water is coming together and will be separated here. So the oxygen will be vented outside, to the outside, to the atmosphere. And the pumps and the heat exchanger bring the water in the right temperature to the electrolysis stack, for example. And after the producing of hydrogen, it is also catched up by the hydrogen and water separator. And after this, we needed deoxo, an especially dryer unit, which brings or refine the hydrogen in a better quality, which leads finally to the compressor and could lead to the pipeline system or storage, for example. And we also have here some different auxiliary units, for example, rectifier transformer, and so on. And all these components are needed, to make hydrogen from water and electricity. Okay, we'll hand over to Silke again.
Yes, I will talk now about the challenges which we have during an engineering of a plant. So normally, if you do an engineering, you are in a tension field between costs, time, and quality. In a perfect world, you would be on this nice orange dot and everything would be all right. But normally, the world is not ideal and nothing is perfect. And then you are maybe in the smaller triangle under the orange dot. So you are still quick in your process. You are kind of cheap, but you receive bad quality. And then you can't be sure that your plant is already running or will run. That's why you need to change something if you are the engineering manager or the project manager. So normally if you have bad quality, you, for example, start then to hire more people or to put more people into the project so that you can achieve higher quality. Then you would go a little bit more up and you would be in the right of the two triangles. You would have now good quality, you are still quick, but it's now more expensive because you hired more people and you maybe decided that you need additional equipment or equipment which is now more secure and has more features. So if you would like to go more to the cheap, again to a cheaper project and to a cheaper plant, you maybe can, you maybe take a few people out and then you are slower. So in the end, you are always in this tension field. And as a good project manager or good engineering manager, you have to find your way through this tension field. And by that, you will always do some compromises. On the next slide, I will show you one example we had during the engineering of the pilot plant. As you can see, we have here a heat exchanger. The heat exchanger is cooling water fluting through on the one side, and on the other side, we have a mixture of glycol and cooling water. When we started with the engineering, we had a rough estimation and said, oh, if something gets broken inside the heat exchanger and glycol is then entering the cooling water, we could be up over the limits which are allowed. So let's do a rough calculation. And the rough calculation said, no, everything is all right. Don't worry. We are under the limits. Everything is all right. Then we went forward in the engineering, and the pipes had been dimensioned. So the diameter was fixed, the content of the glycol was more fixed, and now we had been able to calculate really in detail how much glycol is within this cooling water loop. Oh, then we found out we are over the limits. So first idea was, could we maybe lower the pressure of this glycol cooling water system? So if we have a broken heat exchanger, that the pressure is lower than the cooling water pressure, so that it's possible that it's not possible that glycol is entering the cooling water and then in the end the EMS. So unfortunately, that was not possible. So another round was made, and we were thinking of, oh, is it possible? Could we maybe reposition the pipes so that we have a smaller value and that we then don't, that we are then not over the limits? But unfortunately, that was a real big thing because we had been through a lot of engineering work, and if you would reroute the pipes, it will cost lots of money because there are another pipes in our plant, and there was not so much space for rerouting these heat exchangers. These pipes. So in the end, we gave the manufacturer of the heat exchanger a call and asked him if it's maybe possible to install a double-walled construction. Because then if something gets broken in the heat exchanger, there's a safety room in between, and it's not possible that the glycol is entering the cooling water. It's in a kind of room in between. And we had been very lucky. We had just before the manufacturing process, it was just in time, and the manufacturer said, oh, it's not a big deal for me, we can do that. And in the end, it was kind of cost impact neglectable. And for the next heat exchanger with glycol for RWE, we will think of this solution in the beginning and won't need again the cycle through all the options we went through. Manuel, I think it's now your turn again.
Yeah. I will go through this next slide. So regarding to the available time, I guess I should shorten a little bit up this part here, for example. I will only say, as I mentioned in the beginning, that it's needed from the side of the EU that we have to prove that our process will not be higher than a limit which is coming from the EU taxonomy. And this means, for example, we have to consider that 3 tons of CO2 should not be higher this value by producing 1 ton of hydrogen. And in this process, we have to consider also different ISO norm rules. For example, what I want to say with this slide is that we are in progress, for example, with a kind of plant together with, for example, some supporter like Green Delta, which who are able to calculate the CO2 content of our plant in different scopes we need. For example, one part could be the scope 3. This means the pre-chain emission of the overall electrolyzer system should be included. And also, for example, with the scope 2 part, it should also be include the energy distribution or the used energy for the process. This includes the energy distribution, the losses of the energy distribution, the losses of the energy generation, and so on. And on the next slide, I will show, a lot of different parameters are needed. Yes, you can see it here in the middle. You have different stack lifetimes, you have a different plant lifetime, and based on the electrolysis capacity, you use a specific energy demand or energy demand you have with your plant. You can also varying the operation time per year, for example, and we have also some factors for the degradation rate you have to use. And you can see it here on the picture on the right. Here is the overall process of these electrolyzer process, and so different losses are considered in this field, and they are needed in the end for this process, for this LCA process or this model. Only to shorten this here very up, here you can see in the middle, you see what is which kind of parameters are needed for this model. So as I mentioned on the last slide, you need the process parameters for water, for energy, and so on. And also the material distribution for one stack is included in this process here for a model or for 1 megawatt PEM electrolyzer, which has to be scaled up in the end to 100 megawatt in our case. And it's needed that you have to use here different other parameters like for the plant, for the equipment, so the material for the pumps and the vessels and so on and so on. Yeah, we're coming up to the last part, to the permitting.
Yeah, so we can switch to the next slide, please. So we are talking a little bit about permitting. So this is besides the challenges of engineering, we as RWE have also challenges in permitting. If we would like to start a project on the 1st of July, in 2023. It, in the end, takes us over 3 years till we are at the final point of decision. That has several reasons. So to speed it up a little bit, one of the reasons is that it takes us, for example, 1 year in the permitting planning to map all available animals and plants which live on the site where we would like to build an electrolysis. We need to talk to different experts about noise, about the environment and all these things. We have to do a really huge documentation before we can skip that to permission, and the permission phase, which takes 9 months, is done by the authorities. There they check everything for completeness, they check the impact on the environment, and after that there's still till the decision that we can really build the plant, there's still some time where there's time for complaints. So because everything is shown to public, it's still possible that someone takes his part and complains, and then we are not able to build that plant on the site we wanted to. Okay, so then we would like to sum up our summary. So maybe next. So as we said, RWE wants to install 2 GW of electrolyzer capacity till 2030. We see a market of 113 terawatt-hours energy by green hydrogen. Every electrolyzer technology is driven by its own material-based cost structures, as Manuel explained it, for example, the iridium. The pilot plant is our first little step, but there will be lots of steps who will follow, hopefully. Engineering is always a process field of a field of tension between time, cost, and quality. And the chosen parameters for the life cycle analysis have a big impact on the life cycle analysis. And from the point of view of RWE, we would like to reduce the permitting phase so that we can start up earlier with our construction of plants. So thank you very much for your attention, and we'd like to discuss after the second speech with you.
Okay, Silke and Manuel, thank you very, very much for this very interesting presentation from, let's say, the activities in RWE. And let's say I had a chance and the honor and the pleasure to visit the site in Lingen a couple of months ago. And I was really astonished about the plans and the activities which are, let's say, ongoing there. So maybe we can deepen this a little bit also with the challenges and, let's say, the non-technical barriers which are, let's say, there to avoid such a progress and such a transition. Because I guess this is not necessarily only a problem of Germany, it is also a problem in other countries where we do have already structures, and this structure has to overcome if we, let's say, move towards a, let's say, different system and another system. And on this background, it's also my great pleasure now to introduce Dr. Monshi Marsuk. I hope that I pronounced the name in the right way. So if not, please apologize, because my ability to, let's say, talk with this, let's say, Arabic names in the right way is sometimes a bit challenging. Sorry for that. So he's the former Tunisian Minister for Energy, Mines and Energy Transition, and he will give us an update about the role of green hydrogen in the Tunisian energy strategy. And there we get also an update about the challenges which are most likely also exist in a country like Tunisia, and where you do see the role of green hydrogen in the energy system. So, Dr. Marsuk, the floor is yours, and we are very much interested in your presentation. Please go ahead. Thank you.
Thank you very much. Good afternoon, everybody. Guten Tag and alle Teilnehmer. I thank you. I would like to thank organizers for my invitation to contribute to this webinar series regarding hydrogen economy. The topic of my presentation is the role of green hydrogen in the Tunisian energy strategy, or which role hydrogen can have in Tunisian energy strategy. To try to answer to this question, I think it will be useful to introduce first the hydrogen role in global energy transition. Second, I will briefly present some countries' hydrogen strategy and some aspects of international hydrogen economy, and then I move to discuss the role, which role hydrogen can for Tunisian energy strategy, and I end my speech with some remarks and recommendation. For the first item, in fact, for the first point, I will discuss 4 elements regarding the role of hydrogen in energy transition. The first one is regarding emissions reduction. Second is the role in energy system. Then we take a look at current and future investments in hydrogen. And the fourth element is about application hydrogen and use. In this slide, as you can see, the cumulative, according to International Energy Agency, the cumulative contribution of emission reduction of hydrogen between 2021 and 2050 is close to 60%. It's low compared, for example, to renewable, which they expect 35%. Yes, there are a delay in time between the introduction of hydrogen and renewable. We have a long track since the introduction of renewable, and they play a very important role in power renewable. We've found also technology performance 13%. Electrification expand the usage of electricity is close to 20%. In the next slide, also estimation for the year 2050 by IRENA, International Renewable Energy Agency, and they expect that by 2050 the hydrogen will contribute with 10% in emission reduction, while renewables by 25%, energy efficiency by 25%, electrification by 20%. If we move to contribution of energy usage, energy consumption, and if we consider total energy consumption, the International Renewable Energy estimate that by 2030, the direct use of hydrogen and e-fuels will contribute to 3%, and it will be around 12% of hydrogen contribution to final energy consumption. And we can, in the next slide, in fact, see many estimation of the contribution and expectation of the contribution of hydrogen, which is ranking between 7-8% to 20% by different bodies. If we regard now the investment side in all transition technologies, also said BNF, Bloomberg, also hydrogen has been identified as a key technology for the energy transition. It has so far attracted only a fraction of energy transition related. This fraction is around 0.1% of total investment in energy transition. And we can see that the more important is in electrified transport, renewable energy, and energy efficiency. And if we consider at countries level, we see that in the top 3 we have China with a lot of investment in renewable energy and and electrified transport. Same thing for United States, the second, and Germany. And if we consider European Union, the whole amount of investment is around $180 billion. If we see or take a look at the expectation of investment that should be triple for the rest of the 90s to get on track for net zero scenario, and we see that the most investment will go to electrified transports, renewable energy, and heat, and so. But there are an increase of investment and hydrogen. We expect an increase of investment in hydrogen, but still, I think in the 5 or 4th or the 5th position behind renewable energy, electrified transport, and so, and electricity grids. Now I move to application of hydrogen. Bloomberg categorized or considered 5 categories: sectors where cannot decarbonize without using clean hydrogen, like ammonia production, oil or refining, methanol production. Then the second category is high potential sectors need a low carbon price to adopt hydrogen or other methods of CO2 removal cost more, like steel production, aluminum production. Then the medium potential is when I found hydrogen competitive in some circumstances, like peaking and seasonal usage in power generation, ships, aircraft. Low potential in trucks, buses, heating homes, cement, and uncompetitive, according to Bloomberg, in passenger cars. Also, ENL discussed which more efficient for some application between electrification or green hydrogen for industry, transport, and so. I move quickly because I have a lot of slides to show you today. I move to the second section of my presentation regarding national hydrogen strategies. And as you can see in this map, there are more than 30 countries adopted or published their hydrogen strategies, and we hope that Tunisia will do it this year. Then the first, in fact, case of hydrogen strategy, I take our neighbor and sister Morocco. They, in fact, the advantage as quoted by the document from Morocco Ministry, the advantage of Morocco for hydrogen production, or the ambitious target for renewable energy or power renewable, it will be more than 55% in 2030. The second, the geographic position close to Europe, and the already existing infrastructure for ports and gas, and also for, I think, for a grid. Here I have one remark. In fact, Morocco, they estimate the targets for renewable in power in mix of capacity, and as you know, mix in capacity is higher than the percentage of the mix in generation. I think 52% of a target of 52%, it's close, I think, to 35%. In fact, it's been between 35 and 40% in generation. Morocco, in their design, their strategy, they considered 3 steps. In the first step, usage of hydrogen in local industry, its exportation also of hydrogen, green hydrogen product, and in some countries like Australia, Morocco try to exploration of natural hydrogen deposits. In the second step, Morocco will launch the first viable and cost-effective hydrogen projects, continue exportation of e-fuels, and usage of hydrogen for energy storage. And the third step, the growth and increase the capacity of hydrogen production and e-fuels and usage of hydrogen in local industry, transport, and urban mobility. The second case I considered is Germany, but I will start by European strategy in integration of hydrogen and hydrogen strategies, as mentioned by Kadri Simpson, the Commissioner for Energy in 2020. It's based on 3 pillars. The first one is more efficiency, circular, and sufficiency, sobriety in French, and consume less resource. Second is based massively increase the share of renewable energy in European system. This is easy to do through direct electrification, as the power sector is far ahead of others in decarbonization. And the third pillar is where electrification is not possible or is too costly, we need clean gases and fuels like hydrogen, biofuels, and biogas. In this way, we gradually phase out natural gas. I take the case of Germany, and we start with the very ambitious climate protection package of Germany for renewable energy by a target of 80% of renewable production by 2013, mainly based on solar, with 200 to reach 215 gigawatt. At 15 gigawatt, I remember you that all the capacity of Sterg in Tunisia is 6 gigawatts. So Germany plan to have 215 gigawatt by 2030 for solar, and 115 gigawatt by 23. And we found also in this package the hydrogen, where Germany planned to have a capacity of 10 gigawatt, as mentioned in the first presentation today, in this by 2030. This German's hydrogen strategy is based on production, encompasses many sectors, production, transport sector, industrial, and very important for us is international cooperation with 2 billion in funding for pilot projects in partner countries. If we take, in fact, the potential of the countries' potential to be a good, to make a good cooperation, international cooperation with Germany, and to be a good exporter to Germany, it's based on 2 parameters: energy policy, economically framework 2030. It's based, in fact, in renewable energy studies and targets, political about hydrogen, quality of bilateral relationship, and so, and also the cost of to produce hydrogen. And we found that Tunisia is in the third strip behind other countries like Morocco, Australia, and also in the first strip we found Spain, or where we find Spain and Norway. I hope in the future Tunisia will be in the second one, as it was, I think, in the first presentation of Germany international partners for hydrogen imports. Then I move, in fact, to provide you some, in fact, aspects of the draft published by Department of Energy, U.S. Department of Energy regarding U.S. hydrogen strategy and roadmap, and the clean hydrogen will be developed in waves based on the relative attractiveness of hydrogen application. And we can see that they, for the first wave, they put four lifts, refining, clean ammonia, heavy-duty trucks, off-road vehicles, transit buses, but for example, methanol production, it's between the second and the third waves, and power to liquid fuels, it's in the third waves. And we can see in the next slide better this, in fact, breakdown of usage according to the cost of green hydrogen, and we found that the amount that United States plan to produce according to application and the price of hydrogen. And we see therefore heavy-duty vehicles starting from $4 per kilogram until methanol and heat, when hydrogen should reach less than $1 per kilogram, and United States plan to reach in a decade $1 per kilogram for hydrogen production. The third section of my presentation is regarding the global hydrogen economy. Three challenges, important challenge to or facing hydrogen economy. The first is scale. In order to move to around 100 million ton by 2030 and exceed 500 million ton of green hydrogen by 2015. The second, cost, because green hydrogen, the cost should or could drop below $2 per kilogram in 2013 and $1 per kilogram by 2050. Remark, grade hydrogen production cost currently is ranging between $0.8 and $2 per kilogram. And as you know, the electricity price is the main cost component, accounting for around 58%, and the electrolyzer capital costs at 25%. The third one is trade of hydrogen, international trade, and IRENA expects that around 1/3 of clean hydrogen production to be traded through a cross-border exchange. And we see in this map, in fact, where the optimal renewable resource areas, the optimal low carbon resource, and optimal renewable and low carbon resource. There are mistakes here, in fact, South Africa and not North Africa. And the next slide provide some expectation or some estimation of forecast for production of hydrogen and the cost. And for example, for North Africa, they estimate that the potential is close to 600 million ton by 2050, with a price between $1 and $1.2 per kilogram. I think it's very difficult because they say 597. It's very difficult to be very accurate for 2050. If we focus more on Africa, CVA Consulting identified 3 hubs with qualified hydrogen production with capacity of 50 million ton by 2035. The first one is Northwest Africa hub, Morocco and Mauritania. The second is Egypt, and the third is not in fact in order. And the third one is Southern Africa hub with a production of 70.5 million ton. For CVA, the key success factors for hydrogen industry and hydrogen policy is to activate national planning and incentive schemes. Second, successful pilot projects at demonstration and commercial scale. And third, the demand, aggregate mass scale of take and demand. Here is a map published by World Energy Council And we see here until 2014, they consider that Tunisia will be neutral. I think because the delay in Tunisia to launch our strategy and to launch projects for the production of hydrogen. However, if we take a look at estimation of Hydrogen Council McKinsey company for 2050, that we found that Tunisia will be an exporter for hydrogen to Europe, like Morocco, Algeria, Egypt, and Libya. Here, in fact, I want to share with you some thoughts and remarks. In fact, I found them in Van de Graaff paper in IMF Financial and Development of IMF in December 2022. First one, hydrogen and its derivative could usher in a reconfiguration of energy trade relation. Some regions, notably in Europe and Northwest Asia, are gearing up to become major importers of hydrogen. Others dream of being major exporter or even, as in the case of Australia, renewable energy superpower. Fossil fuel exporter like Australia and country in MENA have several advantages. They can build on their existing energy trade relations, skilled workforces, established infrastructure to become exporters of clean hydrogen. It's an attractive way for them to diversify their economies while retaining their roles as energy exporters. However, it will be foolish to think that hydrogen rents will replace fossil fuel rents or give these countries the same geopolitical leverage. Unlike oil and gas, hydrogen is a manufactured product. It can be produced wherever you have electricity and water. Hydrogen, and finally, hydrogen could be more of a geopolitical game changer for countries that currently depend on fossil fuel imports, but have ample renewable potential, like Chad, Morocco, Namibia, and I hope so on, Tunisia. The Oxford Institute for Energy Studies has established a list of items or criteria in order to be a good or to have a good potential as hydrogen imports. And they compiled Morocco, Ukraine, Norway, Russia. These items are very important for us in Tunisia to improve our ability to develop, to produce and export hydrogen, decarbonization of energy systems. So we have to accelerate our renewable energy plan and to expand it. Water availability, it's the problem for all the MENA region, and we have to launch plans to, for example, desalination. Proximity of hydrogen demand to center. I think MENA is, and in particular, North Africa is close to Europe, and we have some gas pipelines with Europe. Gas infrastructure, geopolitical and security of supply, and planned hydrogen projects. I think it will be the case in Tunisia in the near future with our strategy and the launch of the first pilot projects. I will not discuss, in fact, economy test, but it's very amazing. But I move towards which role of hydrogen in Tunisia energy strategy. To remember, as stated by the ministry this month, our hydrogen strategy is based on 3 pillars: efficient primary energy demand management with the target of reduction by 30% in 23 and 37% in 2035. Second, to boost and accelerate the renewable energy program to install a renewable power capacity more than 8 gigawatt by 2035 is very, very ambitious. And we noticed here that the target is of capacity and not of mix or percentage or share of our production of electricity. Set up favorable condition for the development of new energy transition technology, mainly green hydrogen. We can find other details in the, provided by the ministry in November 2022, like the boost of oil and gas exploration and production, implement fair and efficient energy subsidies, and also for other technologies like electricity mobility, smart grid storage, and so. To summarize, in fact, for Tunisia, the renewable energy, our targets from renewable energy, our aim is to reduce dependency on fossil fuel and increasing our energy security. And currently, a strategy for green hydrogen is being developed and is planned to be finalized by this year in order to accelerate the implementation of renewable energy and intends to position Tunisia as exporter of hydrogen. Sorry. We can have other additional, in fact, more figures, sorry, of our strategy regarding energy efficiency, renewable energies, and greenhouse gas reduction, as provided by the very interesting presentation made by Ghalib Enin in January 2023 in this series of webinar. In this webinar series, I will not, in fact, describe all our energy system, but some main figures that about our energy deficit is about 50%, with more large deficit in natural gas than in petrol. Then the major more than 70% of our natural gas or natural gas consumption is used to produce electricity, sorry, which represents 95 to 96%. But what it is very important, it's the electricity in Tunisia represents only 19% of our final consumption. So we have to improve of renewable in our in the production of our electricity, but we have also to expand the usage of electricity in order to benefit more of renewable energy. In the execution and achievement of in our targets, as you know, our target now is 35% for 2030, as confirmed by the ministry last year. Currently, the renewable electricity represents only 4% in 2020, 4% of our electricity production. It's less than 500 megawatt with hydropower, wind, utility scale, and a PV rooftop. And we note here in Tunisia, the auto production, self-generation of electricity is very dynamic, and I think we can go far and in order to contribute more in the achievement in our goals for renewable energy and electricity. In the last of 22, the ministry launched a call for tenders for 720 megawatt for solar and wind, and for authorization scheme and concession scheme. And they also launched new reforms, the launch of the Electricity Regulation Authority, and the development of green hydrogen strategy ongoing work, and grid interconnection with Europe, and particularly with Italy, with a capacity of 600 megawatt. We can compare, in fact, the situation in Tunisia with other North Africa countries, and as you can see in the left side, that the more Mauritania, but it's a small capacity, grid capacity, they reached 28% of generation flow from solar and wind, then Morocco close to 19%, then Egypt 9%, Tunisia 4%, Algeria 1%. Here, in fact, it's very important work done by OCO Institute, and here a summary of strengths and weakness in Tunisia for hydrogen production. First, for electricity, large, low-cost potential for PV and wind, but until now, very small contribution of renewable power. Second, transport, existing pipeline infrastructure towards Italy, but strong dependence on Algeria for transport infrastructure. The convergence with UE hydrogen strategy, until now, we are waiting for our strategy this year. Water, as I mentioned, productive water management plan in place in Tunisia, but high water stress, in particular in northern Tunisia. Socio-economic green hydrogen could be built blocks for decarbonizing domestic fertilizer industry. Hydrogen strategy and economy, first hydrogen projects in planning, memorandum of understanding with Germany, high interest in exporting hydrogen or derived products. No, the weakness is no existing hydrogen projects to date, and political, and compared to other countries, in the region, corruption is lower and regulatory quality is higher in Tunisia. So we are optimistic. High political interest in green hydrogen, existing trade cooperation with United Union. However, indicators show low political stability. There is a high political uncertainty now. Also, there are very interesting and exhaustive work done by GIZ, Études sur les opportunités en matière de Power to X, and they studied 3 scenarios to produce electricity. The reference scenario, when we go from 20 terawatt per year, terawatt hour per year to 50 by 2015. But if we add electrification and hydrogen production, this production could attain 90 terawatt hour by 2050. And if we add also e-fuels, this production go further to 190 terawatt hour, which compared to our product currently multiply by 9 our current production. So it's a huge important transformation of our electricity and grid. However, if we compare, it's the same study. If we compare the production, the potential production with demand, we see that the potential is very, very high compared of local usage in 23 and 2015, even in the advanced scenario. Regarding costs, also in this study, it's between 10 cents in the optimistic in 2030 and less down to 5, and this corresponds about $2 per kilogram to in 2030 to $1 per kilogram in 2050, but this is in the optimistic scenario. Also, a very important study conducted by IRENA and published in January 2023, and for Algeria, Egypt, Mauritania, Morocco, Tunisia, and we can see the potential of production for each country, and for Tunisia is not so bad. Also, they published some estimation of unit cost, which is lower than it's lower from wind regions than from solar regions. We have also, this is scenario planning. Yes, North Africa Quanti Oko Institute from Oka Institute, they also estimate the theoretical prediction and the realistic prediction from North Africa and total supply costs of gas, hydrogen, and transports. And as you can say, for 2030, it's close, mainly for Morocco, Tunisia, and Algeria, it's close, including transport, it's very close to $2 per kilogram. Sorry, €2 per kilogram. Here's, in fact, a comparison done by EUA IRENA in September 22, comparing the production of hydrogen in fossil hydrogen, gray hydrogen, low carbon hydrogen, or renewable, and that the expectation for 2030. Now I move to conclusion with some concluding remarks and policy recommendation. First, green hydrogen roadmaps should be a part of national sustainable development, in particular in energy strategy and climate change policy, carbon neutrality and resilience. It should be developed in a multi-stakeholder approach with a strong and fair social and sustainability standards and criteria. Second, reforming the governance framework to boost renewable energy and green hydrogen production incentives within a high policy commitment, good legal stability, strong rule of law, transparency, and participation. Strengthening the role of the private sector in green hydrogen development, it's strongly recommended to explore new ways to carry out international cooperation projects on green hydrogen by involving the private sector alongside with public central authorities. Green hydrogen as a driver for decent employment and a remedy for brain drain, adopting regional concerted policy within the North Africa, and reshaping Europe energy relationship. Next slide. For Tunisia energy system, massive development of renewable energy and energy efficiency are in the top of priorities. High share of power renewable is a prerequisite for the success of green, is a condition for the success of green hydrogen production. Tunisia green hydrogen strategy should necessarily take into consideration the development of two sectors, one oriented towards the local use and of this resource, and the second, and the more important, towards its exports, especially to Europe. Tunisia should avoid its ammonia imports, currently ranging from 250 to 400 kiloton per year, and even become an exporting country by developing a green ammonia industry. Power generation, green hydrogen as a fuel could become an option to offset the mismatches by managing the surplus electricity generated from non-dispatchable and fluctuating renewable energy resources. However, and give that the storage and distribution infrastructure, as well as the industry hydrogen consuming application, are more developed in Europe than in Tunisia, this sector, the export, should be the first to be considered, since it's easy, cheaper, and faster to implement, because it only requires the build-up of production capacities. The Europe Commission renewable energy power Europe plan, designed by Europe in May 2022, aims by the year 2023 to attain 10 million tons of green hydrogen from domestic production and 10 other 10 million tons from imports in order to reduce natural gas, coal, and oil in hard to decarbonize industrial and transport sector. This constitutes a unique opportunity for Tunisia for a green hydrogen export. And finally, the green hydrogen water footprint has to be addressed, the large-scale industrial development of hydrogen production. And thank you a lot for your attention, and thank you for.
Yeah, Dr. Mongi Masouk, thank you very much for this very interesting presentation about the situation in especially Tunisia. So we still have, let's say, a couple of minutes. We are already quite late, so sorry for that, but still there are a couple of minutes there. And maybe I understood from the presentation from Silke Neuberger and from Manuel Langemann that, let's say, to develop and to bring such projects hardware side forward, it takes quite a long time. I understood that you have to check if there is some, let's say, types of plants and some types of animals where you would like to build something. And I also understood from Dr. Mongi Masouk that, let's say, also in Tunisia, there is ambitious goals to continue with the energy transition. And therefore, from the timeline, if we would like to take it serious with 2050, that we convert our energy system, our global energy system by 2050 into a green energy system, and we see that we have such a lot of, let's say, time lags in between to realize something, then I have my doubts if this is realistic, if we can achieve these goals, even if we put all our efforts inside, because the timeline is like this. So maybe one from you two, from RWE, and then maybe Mr. Masouk from Tunisian side can make a statement about, let's say, the possible timelines and the realistic goals what we have for the time being.
Yeah, so we can both make a remark. So in fact, that's a real problem for RWE. And yeah, at the moment, we take a high risk because we already start during a permitting phase to order the long lead items so that we can be aware, and if everything fits, that we can stay to our goal that in 2030 we install the 2 gigawatts. If we would not take the risk and already order long lead items, that would not be possible. Right. Manuel, would you like to add something?
Yeah, this is a kind, yeah, as you mentioned before, this is a kind of process of the permitting process, and so it could also be happened that we're going in the wrong direction maybe, and so this is, as Silke mentioned, our own risk to bring all these projects forward. And yeah, so you're right, we currently erecting the pilot plant, and I guess the lesson learned coming up from this project, I guess we will use it directly or with the primary issue in the field of operation, and yeah, and I guess also the outcoming lesson learned in case of erection the plant and something like that we can also use as a good information source. And yeah, so this already helped us for the upcoming projects. And yeah.
But do you see it, maybe one question before I come back to the Tunisian situation? Do you think it's realistic that by 2030 you will be successful? Also on the background that I understood that at the moment the delivery time for new equipment is quite long, that you said you have a problem with the materials, what you need for the electrolyzer. So do you think this is realistic, the time plan, or do you have enough also workforce for doing this? People which know what they're talking about when we talk about, let's say, new technologies? Sorry for being unpolite. Huh?
No, everything is good. So from my perspective, it is realistic to achieve this target. And yeah, you're right. There are existing some long lead items issues regarding, for example, typical things like the transformator, or, for example, also the compressor. There could be become in a problematic situation, and but we are also aware of these and took the right decision for this.
Okay, thank you very much for that. So, Dr. Monty Masouk, how you see it from the timeline, if you would like to continue on this, let's say, transformation pathway for Tunisia, and I understood that for the time being, also the usage share of renewables is not so high yet. Do you think it's realistic to achieve these goals by 2050?
In fact, the targets currently for 2030, 35%, 2035, 50%, and for 2050, 80% of renewables. It's very, very ambitious targets, not only for production, but also to adapt, develop, and build the grid in order to be able to integrate this high share of renewable. As you know, currently in the world, the most high, I think it's Denmark with around 60%, but a lot of it is based on hydroelectricity and wind. If we consider solar, I think in the world, the highest one is in California, with close to 20% of share in the grid, because it's very difficult to integrate renewable like solar with high intermittency and also wind. But as you can see, in Tunisia, we have a very dynamic, very developed self-generation sector. And currently, the contribution, the grid contribution come from, for solar, come from self-generation. I think in Tunisia, it's possible to launch a national project for self-generation that can allow or help or support our targets for 23 and for 2035, support our targets. And some studies forecast that the grid can support up to 20% of self-generation from solar if we can complete with utility scale projects, very important utilities, big utility scale projects around 200, 400 and 300 megawatt for solar and wind. We can accelerate, in fact, the share of renewable energy, solar and wind in our electricity generation. And I have as example, Jordan. In few years, they move, I think, from less than 10% to 20% only with solar photovoltaic share. As you know, our capacity is not so high. It's around 6 gigawatt. And so it's not so big capacity nor so big grid. We can work, but they are very ambitious targets for Tunisia.
Okay, thank you very much for this statement, and to the fact that we are running quite late, and so I would like to come to an end, and maybe we make one short, brief final round, yeah, and because I mean I see that we have on one hand side a challenge to get the equipment. I mean, what we have seen in the last 10 or 15 years is a strong ramp up of the capacity for the production for PV systems. So there we have seen that a lot of, let's say, fabrication locations has been erected, especially in China and Southeast Asia, and not in Germany, not in Europe, which is, from my point of view, let's say, wrong development, but maybe this is only a view of a small professor from a small university. And we have also seen a strong development in wind mill production. And when we look in the future and would like to achieve these goals, I mean, then we have to strongly expand these production schemes for PV systems, for wind systems, and additionally for electrolyzer. And additionally, we need a person, the people, the engineers, you know, who can, let's say, manage this and develop the systems. So from that point of view, also from the infrastructure, what you have to develop to ramp up this in the next couple of years, what do you see for the next 10 years are the most important measures which should be taken that such a development is possible? So maybe we can do this with 2 sentences and then we come slowly to an end. So I will start with ladies first, if this is fine with you, Silke, and then I will.
Yeah, it's fine.
Yeah.
Of course, you have to do a good job to give us the engineers. So as you are working at the university, it's you and also we as a company who would like to recruit lots of people, of course, to fight against this challenge. So from my perspective, one big thing is the engineers and all and their work, and on the other hand, the materials, so that we have all the materials which are needed for the great electrolyzer in the end.
Okay, thank you, Silke. Manuel?
Yes, as you mentioned before, so this overall field is growing up. So this means in the last year or years, we saw that a lot of different new companies who are coming up, who are related to the hydrogen plant or hydrogen systems. And so for us, it's important to have an overview about this. And I could imagine that that we will not get a lack of components or in this field. And so I'm or positive, optimized in this situation, and I guess it will go to a good doing or process.
Let's think positive, because what I see at the moment in the market, that the price for PV systems is going up and not going down, because the demand is so high, you know, and then according to, let's say, what we call Marktwirtschaft, according to economy, I mean, prices are going up. So I'm not so positive about it, but let's keep our fingers crossed. So, Dr. Mongi Masuk, what do you think in 2 sentences? What is needed for the next 10 years to make this transition happen?
Okay, for Tunisia, first we have to accelerate our renewable energy plans, and we should be based on utility scale and self-generation, which can, in fact, bring a lot of capacity to Tunisia in self-generation, and which is very cost-effective in Tunisia. So we have to reach our ambitious targets for 23 and 2035. Then we have to develop, to adopt our hydrogen strategy and to work mainly for exports. I think, as we can see in Morocco strategy, and it's the viable projects in hydrogen will be started in our region after 2030. But we have to be ready with the framework, the legal framework, with the organization, and with many pilot projects in order to prepare the infrastructure and the regulation to, in fact, develop the production of hydrogen in Tunisia.
Okay, thank you very much. And this has been the final statement. With this, ladies and gentlemen, mesdames et messieurs, senores et senoritas, meine sehr verehrten Damen und Herren, it's a great pleasure for me now to finalize or terminate or close this session. With this, I would first like to thank very much Dr. Silke Neuberger as well as Dr. Manuel Langmann for the presentation about the hydrogen activities of RWE. I would like to thank the former energy minister, Dr. Mongi Marzouk from Tunisia, for his presentation about the situation in Tunisia and the plans. And of course, I would like to thank GIZ in Tunisia for allowing us to realize this webinar with a simultaneous translation. And therefore, I also would like to thank very much Madame Shiraz for translating this, let's say, at least my bad German English into excellent French. So thank you very much for that. And then last but not least, I would also like to thank Felix Mendler and Wolfram Tuschewitsky for realizing that everything runs smoothly and without any major problems, and that everybody is well informed and get the link. So this is indeed also quite some work which is done in the background. Thanks a lot for them, both to this. And last but not least, of course, I would like to thank the different organizer from Hamburg University of Technology via the VDI here in Hamburg, as well as the Green Hydrogen Association with Shokri Aslush, as well as the University in Carthago, and of course, GIZ for making this possible. Thanks a lot for that. And with this, I finalize this meeting. But before I switch off, I just would like to mention next week, same place, same time, we will have a presentation from Dr. Genevieve Sauer from NREL in Golden, Colorado, about the situation in the US and the activities in the US in the field of hydrogen, which I hopefully will we will learn quite some new activities. And additionally, and this is an extremely great pleasure for me to introduce the Professor Dr. Sally Brooker from New Zealand. She will give us an update about the situation in New Zealand, what's going on. For her, it's in the morning at 7 o'clock, so she has to stand up early. And from that point of view, everybody is strongly invited to come, that it's worth for her to stand up early and to give us the presentation, the update about New Zealand. With this, thanks a lot again. I wish you a beautiful evening. Enjoy yourself. And thank you very much again, especially to the speaker of this night. Bye-bye, cheers, and see you next week. Same place, same time. Bye-bye.
Bye-bye.